Good day. It's good to be back with all of you. Today, we're going to start talking about a new concept called power series. That's a topic I really enjoy, and I'm looking forward to talking to you about it here, especially because we're going to try out a new approach. So we're unveiling this um, pedagogy, this approach to power series for the first time in the history of the universe, apparently. So this is our first lesson on this idea of a power series. I'd like to start by introducing them at a little bit of an intuitive or maybe even a picture type of level. So intuitively, a power series is like an infinitely long polynomial, except that polynomials are defined so as to have finite length. So here's some examples of those infinitely long polynomials. So notice here, you have this f of x, and it's a polynomial because you have these terms like x to the 0th power, x to the 1st power, x to the 2nd power, x to the 3rd power. We're adding all the way along. So notice that there are coefficients in front of each of these terms. Coefficients 1, 2, 3, 4, 5. And the dot, dot, dot tells you we're going to keep on going with this pattern forever. So you might say, well, what are the next terms going to be? So the next term is going to be like a 6, x to the 6th plus 7, x to the 7th, et cetera, et cetera, et cetera. Like if we went out n terms, we would have n x to the nth. Now, when you have this n x to the nth term, when you're able to write the nth term in that nice clean notation, then we can summarize all this stuff in the nice clean sigma notation, where we'll go from, we'll have an n x to the nth. So this is the same bit that's happening here. Ooh, there's actually something a little bit wrong. Maybe you can already see it. 1, 2, 3. You'll notice there's something wrong in my notes. Ooh, Dusty, what did you do here? You'll notice that this is supposed to be, this is power 0, power 1, power 2, and then I skip 1, power 4, 5. So this is apparently a little bit of a typo that I'll have to fix. So this is 4x cubed, 5x to the 4th, 6x to the 5th, 7x to the 6th. So this term out here should be, so the power, or the number in front is always 1 more than the power. So if we did n plus 1 times x to the n. So sorry about the confusion. I'll have to fix the typo. N plus 1 x to the n. We could ask, what's the smallest of these powers? The smallest of these powers happens right here, where our n equals 0. We'll go from n equals 0. And then we also see this thing is going to end with a plus dot, dot, dot. So we're going to continue this way forever and ever. So we're going to go all the way up to infinity. So this is an example, f of x is an example of a power series. Notice the left side here is the power series, but it's the power series spelled out term by term. And then the right side is the exact same power series. It's just now written a little bit more concisely. So it's 2 ways of writing the same thing. So there's our first example. In our second example, we have g of x equal to x minus x cubed plus x to the 5th minus x to the 7th plus x to the 9th minus x to the 11th plus dot, dot, dot. So we might make sure we're seeing the pattern. So this would continue. The next term out would be a plus, and it looks like we have x to the 13th, and then it would be a minus, x to the 15th, and then it would be a plus, et cetera, et cetera. So the signs are alternating, and the powers are going up by 2 at a time, and they're always odd numbers. They're always odd numbers. So notice what our coefficients are. If we wanted, we could write this thing out, including the missing terms. So this would be like saying the g of x equals 0 plus x plus 0x squared minus x cubed plus 0x to the fourth plus x to the fifth. Do you see what is happening here? We are adding in 0 of all the even terms. Okay, so half of our coefficients are 0, and the other half alternate between plus and minus 1. So there's our power series. If we wanted to write this concisely, we would do it as follows. So we would say this thing is equal to the sum, and we know that our coefficients are alternating between plus and minus 1, and we remember that minus 1 to a power, so minus 1 is minus 1. Minus 1 squared would be positive 1. Minus 1 to the third power would be negative 1. Negative 1 to the fourth power would be positive 1. And so we're going to put in a negative 1 to some power. This might need to adjust. We'll check in a second. To the nth power. And then we know we're going to have an x, and we want only odd terms. So we'll go 2n plus 1. Or maybe we might have to adjust. And then we need to start our n somewhere. So maybe we will start with the lowest power. We'll just try it out and see what happens. Our lowest power here is at x equals, or x to the first power. So let's try from n equals 1 and see what happens. So when n equals 1, this would be negative 1 to the first power, which is negative, and then negative 1 squared, which would be positive, and then negative. So these signs are exactly backwards. So we'll make a little adjustment to get our signs to work right. So we have negative 1 raised to the n plus 1. And then let's check so we know the yellow part's okay. Let's check the blue part, see how that works. So if I put in n equals 1, this would be 2 times 1 plus 1, or 3. So that'll give me x to the third. And then I iterate, I let n equals 2, and I would get x to the 2 times 2 plus 1, or 5, x to the seventh. So I'm getting the odd terms, but I started at 3 instead of 1. And so to get this to work, we will change this to be the 2, what color? So many color choices. 2n minus 1 for our power. So that says odd terms, but I'm starting at 1 instead of odd terms starting at 3. We also notice there's that dot, dot, dot. So we're going to have this infinite representation there. Okay. So once again, we have a power series representation here. Okay. And we could write that same thing more concisely using this sigma notation. So it's 2 notations for the same thing. In one case, it's really easy to see the coefficients. In the other case, it's really easy to see the general term. But both are accurately capturing the essence of this power series. Okay, h. So h is 1 plus a half x plus a third x squared plus a fourth x to the third plus a fifth x to the fourth plus a sixth x to the fifth plus dot dot dot. Here we once again see kind of a relationship between the fraction and the power. So the power is always 1 less than the denominator of the fraction. And you can see that those coefficients are 1, then a half, and then a third, then a fourth, then a fifth, et cetera, et cetera. And so I hope you can see that we have a general term here of, we're going to have some sort of a fraction. So 1 over n plus 1, x to the n. Okay, and this is going to start at n equals 1 and go to infinity. Let's check it out. So if we put in n equals 1, let's try it out. So if we try n equals 1, then our first fraction would be 1 over 1 plus 1, or 1 half, x to the 1. And then if we iterate, let n equals 2, you have 1 over 2 plus 1, or 1/3, x squared. Oh, notice we missed that very first term. So to make that work, we can come in here and adjust and start at n equals 0. So here's the key idea. Working with power series, and a power series has this form C0 plus C1x plus C2 x squared plus C3 x cubed plus dot 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 Cn xn plus dot dot dot, is first and foremost about finding the coefficients C0, C1, C2, C3, Cn, et cetera, et cetera. Often, at least in this class, we can find some nice formula for the coefficients and simply write the pretty clean notation, the sum from n equals 0 to infinity of Cn x to the n's. But either way, the task at hand begins with finding the coefficients. Let me make the correction. This is C2. And in order to help you see the C's, let's see if we can connect them back to the previous example. So C0 is the number that has no x attached to it. Then C1 is the number attached to the x. And then C2 would be the number attached to the x squared. And then C3 would be the number attached to the x cubed, et cetera, et cetera. And so C, you could see C, you could see that the 1/5 would be our C4, the 1/6 would be our C5. This 1 over n plus 1, that would be our Cn. About now, you might be wondering why anyone would care about power series. So I hope this next example provides a little bit of a graphical connection between power series and more familiar topics. And it's going to require playing around with our Texan friend. So example 1, I want to use a graph to explore the sum from n equals 0 to infinity of -1 to the n times x to the 2n over n factorial. And so I want to introduce, in order to graph this, I want to introduce the idea of a partial sum. Okay, so rather than going all the way to infinity, which is a little bit difficult, we're going to approximate infinity with very small numbers. So for example, we could ask, what happens when we have the sum from n equals 0, oh my gosh, from n equals 0 to, say, 1 of -1 to the n x to the 2n over n factorial. So if when n equals 0, this would be -1 to the 0, which is 1, x to the 2 times 0, which is 1, over 1 factorial. This is 1 times 1 over 1, which is just 1. That's going to be the n equals 0 term. And then plus, because it's a summation. And then we have -1 to the first power, which would be -1, x to the 2 times 1, or x squared, over, oh my gosh, just so many typos, it's terrible. This is supposed to be 2n factorial. 2 times 1 factorial would be 2 times 1, or just 2. Okay. I don't know if, I don't recall off the top of my head whether people have used factorials. So if we have 5 factorial, this would be 5 times 4 times 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. 3 factorial, 3 times 2 times 1. 2 factorial, 2 times 1. 1 factorial, 1. 0 factorial is defined to be 1. And then n factorial would be n times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. So all the way down. So that's when, this is what happens when we end at 1. What happens if we end at 2? So if we end at 2, we're going to go from n equals 0 to 2 of -1 to the times x, -1 to the n, x to the 2n over 2n factorial. And the first two terms are going to be the same. We're going to get 1 minus x squared over 2 plus, and then we'll get -1 squared, which is 1, times x to the 2 times 2, or x to the 4th, over 4 factorial. That would be 4 times 3 times 2 times 1. That's 24. Okay. That was when we went to 2, 0 to 2. Let's do one more term. So if we had the sum from n equals 0 to 3, we'll have of all this stuff, -1 to the n, x to the 2n over 2n factorial. It's going to be 1 minus x squared over 2 plus x to the 4th over 24. And then it's going to be minus x to the 6th over 6 factorial. So that'd be 6 times 5 times 4 times 3 times 2 times 1, which is 720. Okay. And we start to see the pattern emerge. So let's look at this graphically to try to understand how it all plays out. So I'm going to try to graph all of these shapes. So first, I need to make sure that I'm back in my normal function mode. And so y1 is going to be, guess we had 1 minus x squared divided by 2. Okay. And we could just graph this on a standard window, and we get a frowny parabola. Okay. Not clear what's going on yet. So let's graph the next term out. So it would be 1 minus the fraction x squared over 2. And then we're going to add a new fraction, which is going to be x to the 4th over 4 factorial, that was the 24. Okay. Okay, so the blue one's here in the middle, and then the red one kind of curves. Interesting. Let's do another term. So we have 1 minus x squared over 2 plus fraction x to the 4th. Oops. Come on, little buddy. Over 24. Okay, but now we got to add, subtract. The next term will be minus because it's going plus, minus, plus, minus, plus, minus. And then this one will be x to the 6th over 720. 6 times 5 times 4 times 3 times 2 times 1. Okay. That's kind of funky looking. Still not clear. Let's do another one. This time, let's see if we can graph with the factorial itself. So it'd be 1 minus x squared over 2 plus x to the 4th over 24 minus x to the 6th over 720. And about now you're thinking, man, those numbers are getting really big fast. So what could we guess? We know the next one's going to be plus. We know the numerator is going to be x to the 8. How about that denominator? Instead of finding, instead of like multiplying it out, 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, getting a big number, let's just type 8 factorial. So that would be 8, and then we go to the math menu, and I think it's under probability. Probability, and there's that 4th option down will be the factorial. So we have our y4. So let's look at the graph. We can even, I think we can even do this faster. So if we wanted to graph y to the 4th, notice each time we're just grabbing the previous thing and adding one more term. So we could graph y to the 4th. So that would be, I think, alpha f4. And then we want y4 of x minus, it's going to be x to the 10th over 10 factorial. 10 factorial starts to be a really big number. Okay, is our graph looking better? I think maybe we'll do one more after this. Oh, look at, do you guys see this pattern where there's kind of this swirl thing happening? Let's do one more. So now we're going to do y to the 5th plus another term. So I'll go green f4, y to the 5th as a function of x, and I'll add fraction x to the 12th over 12 factorial. And here's our last graph so far. Whoa. Now you start to see what's going on. Do you see this? Let's Let's see if I can find the right spot. So drawing, text. You see there's like this shape that, like all the stuff that's happening in the middle right here seems like the more we go, the more like of this up and down thing we see. And if you look at it, you'll notice that it's going right through y equals 1. The low spot is y equals -1. And you might even notice that this bump appears to be right around 1, 2, 3. And then the bump on the other side is somewhere around -1, 2, 3. It might start to remind you of a function that you've seen before. It might start to remind you of the cosine function. So let's try graphing the cosine function and seeing what happens. So if we just add one more line, just do cosine of x. Let me make sure I'm in radians. Yep, I'm in radians. And I graph. And you'll notice that all those funky polynomials are starting to look pretty doggone close to this cosine function. The more terms we add to our polynomial, the closer our approximation will get, the better it will be farther out. And so what we can see from this example is that these power series provide a way of representing functions that don't require anything magical. Like you could evaluate these power series approximations, these partial sums, if you will, by hand. Like it would take a long time to do squares and fourth powers and sixth powers and do all that division, but you could do it by hand. It could give you a way of evaluating the cosine function. And as a matter of fact, the calculator is actually using methods sort of like this when it evaluates the cosine function when you hit that cos x button. So it's not doing exactly this, but it's doing something along these lines. So again, why do we want to play with power series? Well, one major reason to play with power series is that they give us an alternate representation for some really famous functions. So polynomial functions can be evaluated using basic operations, addition, subtraction, multiplication, and division, and they can be differentiated and integrated pretty easily. But this is not the same for many other functions, such as trig, exponential, or logarithmic functions. So it's beneficial to rewrite a function as a polynomial, or in this case, a power series. This strategy is useful for integrating functions that don't have elementary antiderivatives, for solving differential equations, and for approximating function values. Scientists do this to simplify expressions they deal with. Computer scientists do this to represent functions on calculators and computers, etc., etc., etc. Super powerful, super valuable. The geometric series. There are infinitely many power series, but some are famous enough to merit a name. The first of these is named the geometric series. The next few examples help us understand this very important but basic example. So we will begin with examples without x and then work our way towards an actual power series, that is, that infinitely long polynomial. Example 2, evaluate the following. A, the sum from n equals 0 to 5 of 2 times 3 to the n. So let's just understand what we've got here. So we have 2 times 3 to the 0 plus 2 times 3 to the 1 plus 2 times 3 squared plus 2 times 3 cubed plus 2 times 3 to the 4th plus 2 times 3 to the 5th. Okay, this is going to be some number. Maybe I could crunch it really fast on my Texan friend. So I've got, and there's a common factor 2, so I'll factor that out. So I got 2 times 1 plus 3 plus 9 plus 27 plus 81 plus 243. So I've got 728. In B, I'm going to do something similar. but now I have the sum from n equals 0 to 5 of 2 times a third to the n. So this would be 2 times a third to the 0th power plus 2 times a third to the first plus 2 times a third squared, all the way to ending at 2 times a third to the 5th power. Notice the highest power is showing up there at the end. The lowest power is showing up at the beginning. They won't always match perfectly, as we've seen in our previous examples, but in the cases where you just have a power of n, then they will match perfectly. I guess that n is going to alternate. So the first term matches the lower limit, the last term sort of matches the upper limit. And again, I could evaluate this thing. So this would be 2 times the quantity, 1 plus a third plus a ninth, et cetera, et cetera. So I have 2 times 1 plus, I'm going to write it as 3 to the negative 1 plus 3 to the negative 2 plus 3 to the negative 3 plus 3 to the negative 4 plus 3 to the negative 5 and parenthesis. And I've got a number that's just under 3. So this is approximate. So there's all those fractions. Well, I think, let's see if it'll turn it into a fraction. So it's actually 728. Interestingly enough, the same numerator over 243, or approximately 2.999. Getting pretty close to 3. Example 3. The upper limit in the sum is important. So the upper limit, that's this number up here. And the sum is important. I want to compare the sum from n equals 0 to 50 of 2 times 3 to the n. Notice that's the same argument inside the sum as in part A before, and the sum from n equals 0 to 50 of 2 times a third to the n. And again, this is the same series as in part B in the prior example, except for in both cases, what's changed is that now we're going to 50 instead of going to 5. And I hope it's clear that when I look at the first one, we're going to go from n equals 0 to 50 of 2 times 3 to the n. You start small, things start small at 2 times 3 to the 0 plus 2 times 3 to the 1 plus, but we're going to go all the way out to 2 times 3 to the 50. Okay. 2 times 3 to the 50, let's see, 2 times 3 to the 50. Oh, this is a really big number. According to my calculator, it's about 1.44 times 10 to the 24th power. That's a heck of a big number. And so what I want to point out here is that when I had this 3 to the n, 3 to the n grows really, really fast. And so since 3 to the n grows really, really fast, you can bet that this sum is going to grow really, really fast. And so it seems to be kind of getting out of control, if you will. A word we use in this class is, we would say that this sum is starting to diverge. It's really wild and crazy. But if we compare that with the sum from n equals 0 to 50 of 2 times 3 to the n, this is the other one, previous example, so 2 times a third to the 0 plus 2 times a third plus dot, 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 plus 2 times a third to the 50. Well, let's see what happens with this last term here. So that last term is very, very small. So 2 times 3 to the negative 50. That term is about equal to 2.79 times 10 to the negative 24th. When you have negative exponents like that, this means this number is approximately equal to 0. And so we can add more and more terms. And yes, we are adding to the total sum, but we are adding a very, 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 very small quantity. Ooh, I have a typo here. I'm sorry. It should be 1/3 to the n. There, my bad. This is adding a very, very small quantity. And so we get kind of this impression that when this number is big, like 3, then this sum goes crazy. Big, like 3, implies crazy. But in the other case, if we look at the 1/3, and if we are small, like a third, well, that means things seem nice. You sort of get this hint. Oh, sorry. Small, like a third. And that's going to be nice. Okay, so it gives us a little bit of a hint of what's coming. Again, we don't really even know what big and small mean. We don't really know what crazy and nice mean. We need to do a little bit more work in order to truly unpack this. But it does tell us that the 3 seems not promising and the 1/3 seems somewhat promising. So in the last couple of examples, we were letting that upper limit stop at some number like 50. It could have been 500. It could have been 5,000. But what's more interesting is when we allow that upper limit to be infinite. So, oh my gosh, I have so many typos. This is crazy. So instead of having this be an upper limit of 50, what happens if we have an upper limit of infinity? How would that work? So we gotta be a little bit creative, more than a little bit creative. Well, think back to what we did with integrals first. We don't really like to have infinity in the picture. When with infinities, we like to kind of incorporate limits. So let's take advantage of just kind of our intuition based on previous things we've done in calculus. And so we could say that the limit from n equals 0 to infinity of 2 times a third to the n would be the same thing as the sum from n equals 0. And now I'm going to go to k. Here I have infinity. Here I have k of 2 times a third to the n. But we want that k to be infinity. And so we'll add a limit as k goes to infinity. Okay, sheesh. Let's see. What does this mean? Now we have a finite sum. So when in doubt, write out your terms and see what happens. So I'm just going to ignore the limit for the moment. I'm going to work for a while to separate from the limit, and then we'll come back to that limit in the end. So this would be equal to, let's see, we have 2 times 1/3 to the 0th power plus 2 times 1/3 to the first power plus 2 times 1/3 to the second power, all the way to the last term would be 2 times 1/3 to the kth power. Hmm. At this stage, we're going to play one of the famous math games. We're going to take this whole quantity and we're going to multiply it by 1. Of course, that's not going to change anything. But we're actually going to multiply it by a special one, like a one that's going to have some cool characteristics. So in order to do that, let's start by taking out the 2. So I have 2, and then 1/3 to the 0, plus 1/3 to the 1, plus 1/3 to the 2, plus dot 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 dot, plus 1/3 to the k. So let's see, what's my special one? So the special one that I'm going to use here is I'm going to use the special one that is made up of 1 minus 1/3 divided by 1 minus 1/3. Now, I think that everyone would agree that this is a 1. You might ask, where the heck did that come from? The ones in the numerator and the denominator will always be the same, but the 1/3 is the same as this common ratio that shows up in the original question. So it's 1 minus the common ratio over 1 minus the common ratio. Okay, let's see what happens. So what I'm going to do next is I'm going to distribute in the numerator. So my denominator is going to stay the same. So I'm going to have 1 minus 1/3. But in the numerator, I'm going to distribute the 1 to each of these terms, all the way through that dot, dot, dot. And of course, there's a 2 that's living on the outside of all this stuff. My line's a little bit long because at some point I'm going to have to come back and add a limit. Okay, so when I multiply by the red, I'm going to get the same thing I started with. So I've got 1/3 to the 0th power plus 1/3 to the first power plus 1/3 second power plus dot 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 plus 1/3 to the kth power. Then I need to distribute the 1/3 to each term. So I'm going to come in here, come back here, and now I'm going to distribute the 1/3 to each of these terms in the sum. And so I get negative 1/3 times 1/3 to the 0. So this would be minus 1/3 to the 1. And then 1/3 to the 1/3 times 1/3 to the first would be minus 1/3 squared. And then minus 1/3 cubed minus all the way to the last one is going to be minus 1/3 to the k plus 1. Running out of space. The k plus 1. I want to point out that the green terms are going to the first power, second power, third power, all the way up, and then it'd go to the k minus 1 power, the k power, the k plus power, k plus 1 power. And so there's a whole bunch of terms that are stuck in that dot, dot, dot. And then I hope you could see the really cool thing that's happening. The 1/3 to the first power here and the negative 1/3 to the first power there, those are going to cancel out. The 1/3 to the second power and the negative 1/3 to the second power, those are going to cancel out. All the way to the 1/3 to the kth power is going to match maybe like the last of those dots, so to speak. If there was a 1/3 to the kth power, those are going to cancel out. And you'll notice the only terms that are left are the very first term. Need a new color. The very first term here and the very last term here. So the only ones that are left after all of that simplification. And so we're left with 2 times 1/3 to the 0, that would be 1, minus, I've got 1/3 to the k plus 1, and all this is divided by 1 minus 1/3. Whoa, a whole bunch of that nastiness went away. Now, if we back up a little bit, remember that all this, there was a limit that was out front. So let's go back, now that we've done all this hard work, and add those limits and see what happens. So there's a limit as k goes to infinity. Limit as k goes to infinity, each step. Limit as k goes to infinity. Limit as k goes to infinity. So what is that limit? Well, I think it should be clear that as k goes to infinity, 1/3 to the k plus 1, this is a fraction. So you go, think about those powers, 1/3, 1/9, 1/27, 1/81, 1/243. It should be clear to you that this term here is approaching 0. And so this whole sum is equal to 2 times 1 divided by 1 minus 1/3, that would be 2/3. So that's 2 divided by 2/3. 2 divided by 2/3, or 2 times 3/2 if you invert and multiply, or just 3. Huh. Really close to the thing that we'd found earlier. So we have here evaluated an infinite series. Notice that the 2 that was in the very front here, it hung around all the way to the very end of the question, right? And the 1/3 here also hung around all the way to the end of the question. There's an example of evaluating an infinite series. This is actually a topic that you'll see in the next class, but we're using it because it gives us a pretty direct jumping off point to our power series. So let's reflect on this previous example. So remember that we had the sum from n equals 0 to infinity of 2 times 1/3 to the nth power. Here's the 1/3. Here's the 2. And we ended with this formula, 2 times 1 over 1 minus 1/3. So now when we reflect on that, we should see the following pattern. Notice that the a is like our 2. That's the common factor. And the 1/3, well, that would be our x. And so we should be able to see that just by pattern matching, the sum from n equals 0 to infinity of a times x to the n is equal to a over 1 minus x. So in our case, it was 2 divided by 1 minus a third. Now, thinking back to the example 2, where I had that common rate, in one case I had a common ratio of a third, in another case I had a common ratio of 3, and one of the numbers just blew up, it got really big really fast, and the other got closer and closer to 3, it should be clear that this is not going to be true for all x. So this is going to be only valid for small, whatever small means, x's. So let's keep going forward. So this expression, that the sum from n equals 0 to infinity of a x to the n being equal to a over 1 minus x, is an example of a power series, and specifically it's a geometric series. It equals a number only for those small values of x. Specifically, in this case, when we say small values of x, we're talking about x values between plus and minus 1, not including -1, not including +1. Why would that be the case? Well, for example, if x equaled +1, this would be like saying, remember, 1 to the 1 is 1, 1 to the second power is 1, 1 to the third power is 1, 1 to the fourth power is 1. And so it would be saying a plus a plus a plus a plus a plus a. Of course, that's not going to equal a single number. So this power series or geometric series is not going to equal a single number when x is either bigger than or equal to 1 or less than or equal to -1. When a series sums to a number, we say, quote, the series converges, end quote. When a series does not converge to a number, we say, quote, the series diverges, end quote. So here's our definition. The geometric series. A geometric series is the sum from n equals 0 to infinity of x to the n. That is, it is 1 plus x squared plus dot, 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 plus x to the n plus dot, 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 dot. Goes on for an infinite number of terms. And this infinitely long polynomial can be condensed down into this nice, neat formula, 1 over 1 minus x. But that's only true for these small x's, that is, x's between plus and minus 1. So this formula that we found is actually very powerful, even though it only addresses this teeny little instance. So we're able to modify the formula to find power series expansions of other functions. So let me show you an example of that. So example 5, show that the expression 1 over 2 minus x is equal to the power series from n equals 0 to infinity of 1/2 to the n plus 1 over, or times x to the n, and this is for absolute value of x less than 2. So let's see how this works. So we're going to start with some rearrangement. So 1 over 2 minus x. Well, let's just factor, this doesn't quite match our formula because our formula would have a 1 in that position. Well, how do we get a 1 there? We could just factor out a 2, which would put the 1 where I want it to be. So yay, I now have a 1. But the problem is when I factored out a 2, I had to um, pick up this divide by 2 in the x term. And furthermore, this doesn't quite master our formula. Let me make sure you remember the formula we're working on. Recall that 1 over 1 minus x is equal to the sum from n equals 0 to infinity of x to the n. This is the formula that we just learned earlier. This is what we're referring to. Here's that 1 that we want. But notice there's no 2's in sight. So if we don't like the 2, let's see, we could move that 2 upstairs. So we have a half divided by 1 minus x over 2. Sheesh. Okay. What I want to point out is this x over 2 really could fit in place of the x in the original formula, and so can go into the power series. Furthermore, we could just multiply the whole thing. Remember, we had the other variant of our formula where there was an a in the numerator, and that's just going to put an a out front in each term of the power series. So this will be equal to the sum from n equals 0 to infinity. And then we have a, which for us is a half. So this half right here. And then I want to multiply by the x, and our x is x over 2, all raised to the nth power, like that. And then we could simplify this. Notice this would be like the sum from n equals 0 to infinity of, it looks like you've got 1/2 times 1/2 to the nth power times x to the nth power. And these two terms can be combined to be n equals 0 to infinity. Oh, let's combine them in red still. To be 1/2 to the n plus 1 power. And then we still have that x to the n power. So this is what we were trying to show with one exception. We still haven't shown how we get the absolute value of x is less than 2. So let's see if we can unpack that a little bit. So recall that in this formula that we're recalling, it's true when -1 is less than x is less than 1, which would be the same thing as saying absolute value is less than 1, of x is less than 1. So it's just sort of two ways of writing the same thing. And in our case, what is that x? So in our case, that x, so this would be when our x, which is x over 2, is less than 1. So here's that green bit. Multiply both sides by 2. You get or absolute value of x is less than 2. So we took the geometric series formula that we were gifted in the last section, and we modified it to account for the 2, kind of like for the fact that the formula we're working with is a little bit different. So just a little bit of modification, and that geometric series formula could handle things that didn't look exactly like the geometric series formula that we started with. And we're going to do quite a few more examples that will show you time and time again how powerful this simple geometric series formula is, as long as you're clever with your algebra and clever with your calculus. Example 6. Find a power series expansion for f of x equals 1 over 1 plus x squared. When does this series converge? That is equal a number for a given value of x. Now, one thing I'd like to point out is that this function is that we really only have one power function tool so far, namely the geometric series. So if we want to make this thing look like the geometric series, since it's our one tool, let's play as follows. So we can have our f of x, which is 1 over 1 plus x squared. And this will be the same thing as 1 over 1 minus a negative x squared. Okay. So now it's in the form of, our geometric series, namely the sum from n equals 0 to infinity of a times x to the n equals equals a over 1 minus x. And so here's the x showing up, it's the yellow thing. Here's the a showing up. And so in our case, we recognize that the green thing, the a is going to be 1, and the yellow thing is going to be negative x squared. So this tells us that f of x equals the sum from n equals 0 to infinity of 1, that's our a, times negative x squared to the nth power, which could be written more succinctly as the sum from n equals 0 to infinity of negative 1 to the nth power times x to the 2n power. And here is, again, our a. Here is our yellow x, or our common ratio. Just a little vocab. This bit right here, that x, or the minus x squared, that's what we call our common ratio. You'll learn about this, the common ratio, a little bit more when you study geometric series in Calculus 4. But for now, we'll just give it a label. So there is example 4. Oh, I'm sorry, we haven't fully answered the question. The second part of the question asks, when does this converge, that is, equal a number for a given value of x? Well, since we use the geometric series, it's going to converge whenever the yellow stuff, the common ratio, this converges when the yellow stuff, namely negative x squared, is less than 1 in absolute value. So you want the absolute value, obviously doesn't care about the negative. So this would be when, same thing as saying when absolute value of x squared is less than 1, and x squared is less than 1 in absolute value when absolute value of x is less than 1. That is between plus and minus 1. So here are the x values on which this power series is a valid expansion for the given function f of x. Example 7, integrate the following. Integral of 1 over 1 minus 8x cubed dx. So one thing you might notice is that we could integrate this using partial fractions. So we could factor, do a partial fractions decomposition, and see where that takes us. But since we're learning about a power series, let's take advantage of the power series, remembering that we have, I think it was a green a and a yellow 8x cubed. So we see that this is of that form, 1 over 1 minus x, where in this case the x, or the yellow x, is 8x cubed. And so we could say integral of 1 over 1 minus 8x cubed dx is equal to the integral of the sum from n equals 0 to infinity of, it's a little bit tough to read. Here's that yellow x, so to speak. So we're going to have 8x cubed. Oh, threes are having a hard time tonight, sorry. All raised to the nth power dx. Now, we haven't proven it yet. We haven't even really stated it yet, but proceeding as we would like to proceed, we could intuitively say, if I want to take the integral of this infinite sum, then that would be the same thing as finding the sum from n equals 0 to infinity of the integral 8x cubed all raised to the nth power dx. So that is the, the integral here of the sum is the same thing as the sum of the integrals. And I think we'll see a statement about this in a moment in the notes, but the main thing is that this is a true and valid statement provided all of these sums converge. So if we have nice x's, nice sums, then this is a valid thing to do. So notice from here that the, notice that 8 times x cubed all raised to the n would be 8 to the n x to the 3n. And 8 to the n is a constant, so this would be equal to the sum from n equals 0 to infinity of 8 to the n. And we've got the integral of x to the 3n dx, which will be the sum from n equals 0 to infinity of 8 to the n times x to the 3n plus 1 divided by 3n plus 1. And all of this is going to be a plus c. It's tempting to write that plus c out here, but if we write it on the end, it's unclear whether that plus c is inside the summation or not. And so rather than writing it plus c at the end, in these kind of cases, it makes sense to put it as a c plus right at the beginning. So that's that's my constant of integration. And so the question asked us to integrate this function here, 1 over 1 minus 8x cubed. And we have integrated it. We have found an antiderivative but we have a solution that is represented by a power series. Notice that when we have a power series, we also have to ask, when is this valid? So when is the statement valid? And so it will be valid. So this is valid, or it converges when the yellow thing in magnitude, 8x cubed, is less than 1. Here's that yellow thing again. And in other words, that would be where the absolute value of x is less than 1/8. So we have a power series representation for our antiderivative. We found our antiderivative, way easier than doing partial fractions. It looks like it's just 1, 2, 3, 4 lines. But the kind of the funny part about this antiderivative is we've only got the antiderivative when x is between -1/8 and +1/8. So we've answered the question. I'm not sure how valuable it is, but nevertheless, we have answered the question. So we can begin to see the three main aspects of power series all coming together. So the first part is here. It's finding a power series representation for a function, and then we would use it to solve some question. So in the last example, we were finding a power series representation for the antiderivative of some given function. The second thing we have to do is we've got to ask what x values, for what x values is the power series representation? That is, when does the series converge or diverge? So for example, in the last example, we said that our power series was only valid between plus and minus 1/8. And then finally, we've got to prove that all this stuff is legitimate mathematics. And this last step is mostly beyond the scope of highline math. We're going to touch on it a little bit. We will probably leave the finer details to another class, possibly a class well beyond highline. So most of our effort is really going to be spent on these first two steps here of finding that power series representation and determining the x values for which the work is valid. As we assumed in the previous example, one of the qualities of power series is that they can be manipulated through addition, subtraction, multiplication, division, differentiation, and integration to find other power series. So, for example, assuming the series behave nicely, that is, converge on some neighborhood, we have the derivative of a sum is the same thing as the sum of the derivatives. So you can kind of move the differentiation in and out. Similarly, the integral of a sum is the same thing as the sum of the integrals. And it was this latter property that we used in example 7. Example 8, show that 1 over the quantity 1 minus x squared equals 1 plus 2x plus 3x squared plus 4x cubed plus 5x to the fourth plus ... This requires a little bit of cleverness. I think we could take it on from either side, the left side or the right side. But maybe we will take it on sort of looking at it from the left side and recognize that 1 over 1 minus x quantity squared looks a little bit like 1 over 1 minus x, except for the denominator squared. Rather than, we could multiply, but rather than, that's going to create kind of a nightmare. So rather than multiplying, let's see if we can create this expression through differentiation. So let's see. So let's notice that if you have the derivative of 1 over 1 minus x, this would be like the derivative of 1 minus x to the -1th. That will be negative 1 minus x to the -2th times -1 using the chain rule. Or in other words, 1 over 1 minus x quantity squared. So notice that the derivative of 1 minus x is 1 over 1 minus x quantity squared. So this tells us that the integral of 1 over 1 minus x quantity squared will be equal to 1 over 1 minus x. Okay. At least within a constant. So we can sort of go either way on this relationship. So if I want to use this, notice it's of course easier to differentiate than to integrate. Let's use this first step here. And the second one is just an observation. We won't need it at this time. So if I want to use 1, we notice that d dx of 1 over 1 minus x equals 1 over 1 minus x squared. But observe that d dx of 1 over 1 minus x is also equal to the derivative of the sum of x to the n, the geometric series. Shocking, isn't it? Geometric series comes up over and over and over again. If you want to differentiate an infinite series or a power series, you can differentiate term by term. So this is the sum from n equals 0 to infinity of d dx of x to the n, which would in turn be the sum from n equals 0 to infinity of n times x to the n minus 1. And if you wrote out the very first few terms, the very first term would be 0 plus 1 times x to the 0 plus n equals 2, so 2 times x to the 1 plus n equals 3, 3 times x to the 2 plus dot, 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 dot. Or in other words, we have 1 plus 2x plus 3x squared plus dot, 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 which is exactly what we were trying to show. Notice once again, this is all coming from the geometric series. Since it's all coming from the geometric series, this is only going to be valid when the absolute value of x is less than 1. Oh, and in case you were missing the connection between these things, this d dx of 1 over 1 minus x, that's the same thing as the 1 over 1 minus x quantity squared. So here's our power series that we've ended up with. So notice thus far we're mostly ignoring this question of when the power series are valid, except for the fact that these have all been related to geometric series, and so we actually have been able to answer the question at least a little bit at a time. Example 9, find a power series representation for ln of 1 minus x. So this is somewhat similar to the last example, except for in reverse. So here, notice that d dx of the ln of 1 minus x will be 1 over 1 minus x times negative 1, or negative 1 over 1 minus x. And so this tells us that the integral of negative 1 over 1 minus x dx will equal the ln of 1 minus x plus a constant. This thing over here on the left side, that's, well, at least inside the integrand, so this stuff right here, this stuff comes from the geometric series. So if we want to find ln of 1 minus x, we could take advantage of this time of line 2. Previous example was line 1. So this tells us that the ln of 1 minus x, which is what we care about, is equal to, there's going to be a constant of integration that we need to remember, c plus the integral of -1 over 1 minus x dx. So I've already accounted for the constant of integration before I started. I could add it in the end, either way. Here's our leading term of -1. Our common ratio is x. This is, shockingly enough, another geometric series. So we have c plus the sum from n equals 0 to infinity of -1 x to the n. Notice this would have to be true, and this would be when -1 is less than x is less than 1, or absolute value of x is less than 1. Okay. I guess I don't need to write the -1 here. So -1x would just be the same as just -x. Notice this is not alternating signs. Every single one of these terms is the same. A couple oddities of this. So if you look at this expression from -1 to 1, so think about putting in -1 into your ln. So at -1, this would be like ln of 1 minus -1, or ln of 2. And at 1, this would be ln of 1, which is, or ln of 0, pardon me. So this power series we're using is finding us values of ln between ln of 0 and ln of 2. Of course, ln of 0 is undefined. So in this particular case, we can actually find our value for c. So to find c, what we're going to, not next to c, next, find c. So to find c, what we're going to do is we're going to say these two expressions must be equal to each other, and so we can evaluate at some special value. So you might notice that if we let x equal it's going to be a little bit of a error. If you let x equal 1, oh, you can't let x equal 1. If we let x equal 0, I'm sorry. If we let x equal to 0, so let's let x equal 0, and then the two sides must be equal to each other. So if you look at this left-hand side here, the left-hand side, you're going to get left-hand side is equal to the ln of 1, which is 0. And then on the right-hand side, you're going to get right-hand side equals c plus the sum of the negative zeros, which is just 0. So you get 0 equals c plus the sum of the zeros. It should be clear from this that c is going to be 0, because you actually have an equivalence. So kind of cool. All told, we were able to find a power series representation for ln of 1 minus x. That power series representation we just found is the ln of 1 minus x equals the summation from n equals 0 to infinity of negative x to the n. And we've discovered that this c is 0 through this process down below. And we've also discovered that this power series is valid on that nice friendly domain absolute value of x less than 1. So historical note. Today we can evaluate logarithms simply by pushing a calculator button. But prior to having calculators, mathematicians looked up log values in books. And so one of the sources of the values in the books was that mathematicians would evaluate power series like the ones below. And so you'd have mathematicians, they would evaluate these power series over and over, not the whole thing all the way to infinity, but maybe the first 5 or 10 terms, just enough to get with the answer they needed. And they would create a value, and then they would look up and they'd find another value. And so they create these tables that could be used. And you can find them, go look at a thrift shop for an old CRC handbook, for example, and that'll show you tables of logarithms. In example 10, we want to integrate the inverse tangent of x using power series. And we could evaluate this using Calc 2 techniques by, I believe, using integration by parts. But here we're going to use power series. And to do that, we're going to remember that kind of a relationship. So recall that the derivative of arctangent is 1 over 1 plus that argument squared. Well, this quantity here, the 1 over 1 plus x squared, might look familiar to you. You might remember it from earlier in this lesson. So from example 6, we had that 1 over 1 plus x squared is equal to the sum from n equals 0 to infinity of negative 1 to the n, x to the 2n, like that. And so if this is the derivative of arctangent, then that tells us that arctangent must be the antiderivative. So arctangent must equal the integral of 1 over 1 plus x squared dx, or in other words, the integral of the power series from n equals 0 to infinity of negative 1 to the 2n dx. Well, that puppy is, we can pull the summation outside, the sum from n equals 0 to infinity of the integral. Ooh, I lost an x. Oh my gosh. Sorry, I got a copy error here. Negative 1 to the n, x to the 2n. So integral from n equals 0 to infinity of negative 1 to the n, x to the 2n dx. So this would be c plus the integral, or the sum from n equals 0 to infinity of negative 1 to the n, since that's a constant, times x to the 2n plus 1, all over 2n plus 1. Notice this needs to be true for all x's. And so to find c, so let's see, find c. So to find c, we can set x equal to 0. And so we know that the arctangent of 0 is 0. And over on the right side, we notice we have a sum of x to the powers. And if we let x equal 0, we'll get a sum of a whole bunch of zeros. And so on that right side, on the right-hand side, we will get c plus the sum of the zeros again. And so since these two things must be equal to each other, we get that c equals 0. So we're not done yet. Okay? All we have shown so far is that the integral of the arctangent of x dx, which is the question we're trying to answer, would be the same thing as trying to find the integral of the sum from n equals 0 to infinity of -1 to the n, x to the 2n plus 1 over 2n plus 1 dx. And so you might say, where is that coming from? So we showed that arctangent of x is equal to all of this garbage down here, the sum from n equals 0 to infinity of -1 to the n, x to the 2n plus 1 over 2n plus 1. Remember, c is equal to 0. And so we're going to replace the arctangent of x in the integral that we care about with the summation we found above, or that we've already found. And now we can find the integral of the sum is the same as the sum of the integrals. The -1 to the n remains a constant. And so now we'll have a new constant. Maybe I'll call this one C1. And it's going to be the sum from n equals 0 to infinity. Still, we've got a -1 to the n. And now we have an x to the 2n plus 2 divided by 2n plus 1 times 2n plus 2. And in this particular case, we're no longer going to be able to just get rid of that constant of integration, find out what value it is, because since we have an improper integral on the left, it makes sense that we will have an improper integral on the right, complete with that constant of integration. So is this better? Is this worse? I'm not exactly sure, but this would be an example of how you could find an antiderivative instead of using the integration by parts. You could do it using power series. I should also comment that this is valid, or it converges, when absolute value of x is less than 1. And the reason I know its absolute value of x is less than 1 is because this formula that we're using is coming from a geometric series that had that same interval of convergence. So as the historical note says, earlier in calculus, we learned to integrate questions like this using integration by parts. Power series provides an alternate approach that requires no calculus skills beyond integrating and differentiating polynomial terms. And so you can imagine, here you are able to integrate things without knowing more sophisticated integration techniques. Pretty interesting and somewhat valuable. All right, last question from this section. Example 6. I want to solve f of x equals f prime of x using power series. This is technically not a traditional calculus question. This is actually a question you'll see kind of in differential equations. But I think it's a nice example because of the fact that it's going to invite us to think about those power series in a term-by-term manner, which is something we talked about earlier, but haven't really touched in quite some time. So this term-by-term approach is going to be a precursor to what we're going to do later on. So let's think about it. If we're working with power series, then that means that f of x must be equal to some c0 plus c1x plus c2 x squared plus c3 x cubed plus dot, 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 dot. Okay, And we don't know what the C0, C1, C2, C3 are. Those are the constants that we need. But if F is indeed this kind of power series, then that would imply that F prime of X would equal, well, we just have to take a derivative. So we would have the derivative of C0 is 0. So then derivative of C1x would be C1 plus, it looks like 2C2x plus the derivative of C3x cubed would be 3C3 x cubed. We start to, or x squared, pardon me. Start to see the pattern emerging. Plus 4C4 x cubed plus dot, 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 dot. And then what we're going to do is we're going to set up a series of like an infinite number of equations. So notice what's happening here. If we match the x terms and the x squared terms and the x cubed terms, okay, even the constant terms here, what that's going to tell us is that we can match the coefficients. So you can see that C0 must be equal to C1. C0 equals C1. And then if you look at the next terms, C1 must be equal to 2C2. C1 must be equal to 2C2. C2 must be equal to 3C3. Okay. C3 must be equal to 4C4. Et cetera, et cetera, et cetera. So what does et cetera, et cetera, et cetera mean? Well, it looks like it means that Cn will be equal to n plus 1 C n plus 1. Okay, let's see if we can understand where to go from here. Let's see if we can put everything in terms of C0. So if we want to put everything in terms of C0, notice we're going to start with C0, and then we know that C1 also is the same as C0. And how about C2? Well, C2 is equal, C1 is equal to 2C2. So we could divide by 2, and so we'd get 1 over 2 C1, or in other words, 1 over 2 C0 for our C2. How about C3? So C3, here I'm looking at this equation. So I'm going to solve for C3. So C3 will be 1/3 C2. And we've already found that C2 is 1/2 C0. So this would be the same as 1/3 times 1/2 C0. Okay. How about C4? So here I'm looking at this relationship. And so C4 would be 1 over 4 C3, and 1 over C3 would be the same as 1/4 times 1/3 times 1/2 C0. I'm hoping you're seeing the pattern here. So it looks like if we went all the way down, it looks like if we went to Cn, we would get 1 over, well, if I had 2, I had 2, which is the same as 2 times 1. If I had 3, I had 3 times 2, 3 times 2, 3 times 2 times 1. If I had 4, I had 4 times 3 times 2 times 1. So you're starting to see factorials. And so Cn would be n times n minus 1 times dot 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 times 3 times 2 times 1 C naught, which would be the same thing as 1 over n factorial C naught. So let's see, and notice every single one of these terms has a C naught in it. So there's like a constant factor. So that tells us that our f of x is going to equal some coefficient C naught, which we don't know, and then we're going to be left with 1 plus C1 is, 1 C naught, so I've got 1x or x plus C2. C2 is 1/2, which is the same as 1/2 factorial, x squared plus C3, which is 1 over 3 times 2, or 3 times 2 times 1, which is 1 over 3 factorial x cubed, plus 1 over 4 factorial x to the 4th, plus dot 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 dot, on and on forever and ever. Or in other words, we've got that this thing is equal to C naught, some constant, times the sum from n equals 0 to infinity of 1 over n factorial times x to the n. And so you have solved this equation up above, this what's called a differential equation, where it is f of x equal f prime of x, and you have a solution without knowing anything else about the equation. Interestingly enough, our f of x, we will play with this. I think you already played with it back in the previous quarter, but you'll play with it in differential equations. And we'll play with it with Maclaurin's series as well. Our f of x here is actually c times e to the x. That's what this, or I guess it'd be c naught times e to the x. That's what this function is that we're messing around with. But we don't need to know that it's c naught e to the x in order to find the power series expression, a solution that we found. So note, in this solution, we took a term-by-term approach to finding the coefficients c naught, c1, c2, c3, dot, 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 cn, etc. That is, we found kind of an expression for each one of those coefficients. This has the same end result as finding a nice clean formula, sum from n equals 0 to infinity of cn x to the n. It's just that the notation where we find all the c's is not quite as concise as the notation where we have the sigmas involved. So, historical note. You may recognize the question above as a differential equation. Power series provides an extremely powerful technique for solving differential equations that can work on many, many questions. It frequently isn't the fastest or cleanest approach, but it works. This is why power series have historically been that Swiss Army knife or duct tape of functions. They work in a wide variety of situations. So there is our first extended lesson on power series. In this series, we learned what a power series is. We learned a little bit about different ways of representing them. We learned, or we talked about how they are a Swiss Army knife or the duct tape of functions, and we learned a little bit about how to manipulate them using algebra, but also using calculus. We wrapped up with one kind of cool example that involved differential equations. So there you have it, the beginning of our understanding in our lessons on power series.